Okay, good morning, everyone. Today we're going to continue our discussion about the linear mixed effect models. So we started our presentation last time by introducing the school effectiveness example. Okay, so let me give you a quick recap. So in this example, the data has a grouping structure, which means that our observations, yi's and xi's, are grouped. They have a natural group relationship. So in here, the groups are the schools. But we are interested in the effect of a predictor regardless of the school, while we want to account for the differences of the schools. So therefore, it makes sense to include an intercept that is school specific. So like here in this model B, we have an intercept with denoted as beta 0 I. I is the ith school. So we are actually saying that, okay, different schools have different intercept, while the effectiveness of the school district, okay, the xi is the predictor, whether it's in a good district or not good district. So we're interested in the common effect beta 1, the effect of school district on students' scores. So in this model, the issue is that we have too many beta 0 i's if our school number is big, because we have one intercept per school, while we may not have so many observations per school. So that will make us have a very heavy estimation burden since we have many parameters. So on the other extreme, we could just simply assume that all schools share the same intercept beta 0. So that will significantly reduce our number of parameters. But this is a very brave assumption because we don't know whether the schools share the same intercept or not. So therefore, what makes sense is to use an intermediate approach. That is, we assume the school intercepts share a distribution. So beta 0 I follow a normal distribution. This is a strong assumption on how the school intercepts are alike. So, or how they are distributed in relation to each other. So we're assuming that they are from one normal distribution with a common mean beta 0. So this beta 0 essentially has the same meaning as the common intercept. But we allow these school-wise or school-specific intercepts to have deviation from beta 0 following a standard deviation of tau squared. So therefore, we, on the one hand, allow the schools to have different intercepts. On the other hand, we try to unify them by putting them under this normal distribution, so that we reduce the number of parameters from the number of schools here to 2 parameters here. So this is a way that can allow us find the balance between number of parameters while accounting for the reality that different schools have different intercepts. And we say that for this type of model, if we want to estimate parameters, including this beta 1, of course, our parameter of interest, and the beta 0 tau square, which are, you can regard them as the prior parameters. If we regard beta 0 I as the parameter, they follow the prior. So in the Bayesian framework. So in that case, if the prior parameters are going to be estimated from our data, we call this approach empirical Bayes. So that's what we said last time. So essentially, you can see the relationship between linear mixed effect models with random intercepts. Here is a special case with random intercepts and its connection to empirical Bayes. So that's why sometimes you'll see people say, okay, they're essentially the same thing. Yeah, it depends on how you regard your model. If you think of this beta 0 i's distribution as prior, yes, then you're under a Bayesian framework. But if you don't think of the Bayesian sense, but just think of this as a 2-layer hierarchical model, that's also fine. Then you are think of this as a frequentist way. Okay, so that's the introduction. And then we introduce the, so we introduce the random intercept model, which is what I just said. So basically, we can say that, okay, the random intercept model is used if you have many small groups and each group has few observations. And here in this model, the only parameter you consider to be random is the intercept. You don't consider the other coefficients to be random. But more generally, you could actually divide your covariates and based on their effects. So for some covariates whose effects are of your interest, you would like to assume their effects to be fixed effects. And these fixed effects are not dependent on the school or the group structure. So you assume this is some effect universal to all the observations. But you may also want to include some covariates whose effects change from group to group. So in this case, you would consider those effects as random effects. So that depends on the school. And that differences among schools need to be accounted for, but you are not interested in getting one parameter per school. So you just unify those parameters by assuming that they together follow a distribution, kind of like the prior. That these are the random effects. So back to that school example, basically here our covariates will include, so for the fixed covariates, it will be the intercept, the common intercept, and the school district indicator. So it will be two columns. For the random covariates, it will be the intercept only. So essentially, you are going to have the covariate for the intercept, you are going to have it appear for twice. One is for the fixed part, that is the common intercept. This is the second part, that is for the variation of different schools. So that's why by assuming that you see this random effect has zero mean, I'm just considering, okay, this is some additional intercept changes that's going to be added to this common intercept. So with this, I can actually write my model in this matrix form. Basically, for group I will have a vector yi, includes all the students in school I, in that example. And this fixed part is the common intercept and also the effect of the school district. And the second part is the small variation in the intercept for school I. So we need to be clear that here, beta as the common effect that has nothing to do with the school, it doesn't have a subscript I with it. But for the random part, delta I, it is the school specific effect. So that's why it has delta I, subindex I. And then epsilon I is just the regular error term. You can regard this as the noise or just the random error. So then in this model, we have two parts that are random. One is this random effect, school-wide random effects. The other is the measurement error. So putting them together, we assume that this is the error, this is the random effects, they are jointly Gaussian because we are under this linear model case. So we are still using normal assumptions throughout. So it's multivariate normal with mean 0, and they have their own covariance matrices and their dependence is 0. Okay, so for the error term, I can assume that the error term of group I has its covariance matrix big sigma I. But for simplicity, we often assume the random errors are IID, right? So then therefore, we can simplify sigma I as a diagonal matrix with lowercase sigma I squared in the diagonal, which means that this is the variance of the random error in group I. And for this omega, it is about the random effect. So we may also give it a simple assumption by simplifying it. And usually, we even want to further simplify sigma I squared to sigma squared, which means that we assume all the measurements across all groups have the same variance in random errors. So if you do have many data points, or if you do have very few data points, you may want to simplify this assumption to further reduce your number of parameters. But it depends on how many observations you have for each group. Okay, so these are the general assumptions for the linear mixed effect model. So by mixed effect, we mean that there is a fixed effect term, there is a random effect term. So they're mixed. So today I'm going to give you another way of introducing the random intercept model. I think it has some very interesting interpretation, which I didn't say last time. So I think it's worth mentioning. So let's just revisit that random intercept model. So I'm going to write it as this. So revisit the random intercept model, short as RIM. So if we recall, based on our two ways of writing this, or two layers of writing this linear mixed effect model, what we could do is that we just give you the notation again as a recap. So we have group I that goes from 1 to n. We have a total of n groups. And within each group I, we have observation J that goes from 1 to Ni, okay? And our model has two levels. So within the group I, so level 1 is within group. We would assume that our response Yij follows maybe let me just put it out straightforwardly. So in that school effectiveness example, we have a group specific intercept, okay, beta 0 I call it this way. And we have a predictor. Let's just call that predictor Xij. Although in that example, all the Xij equal to just Xi because all the students in the same school share the same predictor. But in general, we should write this as Xij. That is, the J's observation in the ith group has its predictor Xij. Maybe I just make it a little explicit, Xij transpose as a vector times beta. So please note that here, the way I wrote it, this term, unlike our regular way of writing this doesn't include intercept because I already put intercept out. So we need to be very clear when we write a linear model about where the intercept is. Okay, and then plus epsilon ij. So here j go from 1 to Ni. This is level 1 within group. And we have a level 2 between groups. Or I should say more explicitly, all groups. So please note that if I treat each beta 0i as a specific fixed parameter, I'm done. I can stay at level 1. That means, okay, I have a lot of parameters in this model to estimate. But adding level 2, by allowing me to group this beta 0i, I can reduce my number of parameters. So level 2 basically says beta 0i equals a common beta 0 plus delta I, okay? And here I go from 1 to n. And within each level, there is randomness. So for level I, the randomness is what? I can basically say, okay, epsilon ij are all IID following a one-dimensional normal distribution with mean 0, variance sigma I squared. And for the level 2, I can assume, okay, the delta I, these delta i's are IID following a one-dimensional normal distribution with mean 0 and variance omega squared. Yeah, you see, I have randomness here, randomness here. So putting it together, if I want to restore my matrix form, then you can see that this is essentially giving me what? Using this matrix form to visit this. Now this epsilon I is a vector that by stacking the observations in group I. So it will be epsilon I1 to epsilon I and I, right? And that's my epsilon I. So putting epsilon I and delta I together. So please note that here I have Ni and I have only one entry. That's how their proportions are. They will be together a multivariate normal distribution with dimension Ni plus 1 dimension normal distribution with mean 0. And now here the covariance matrix would be sigma I squared times an identity matrix with Ni dimension, 0 here, 0 here, and in the lower block, it's just one by one. This is omega squared. So you see how I can connect this two-level model with the matrix notation we have above here. You see their connection. So you see here, the omega is simply a 1 by 1. That's this lowercase omega squared. And this big sigma I is just a diagonal matrix with sigma I squared on the diagonal. Okay, and given this, you see that I can combine this level 1 and level 2 into one model. So you can see it is a linear mixed effect model. So this is a way to, so if we write it this way, this is what we call hierarchical linear model, okay, HLM. And combining levels 1 and 2, we can obtain this so-called linear mixed effect model. That's why we said they are equivalent. So how do we combine them? You can see I can just plug in level 2 into level 1 and I'm done. So I can write Yij equal to beta 0 plus Xij transpose beta plus delta I plus epsilon Ij. And now writing it this way, I will let J go from 1 to Ni and I go from 1 to N. That's it. So you see, writing it this way, I can easily tell, okay, this is the fixed part because it involves no random variable, while this is the random part, right? And fixed effects, random effects, so that's why it's a linear mixed effect model. Okay, and writing it this way, you see, we have a better connection with what's out here. So this is just a scalar form, but if I put it into a matrix form, then what I do is that stack J from 1 to Ni by row. I stack this equation for Ni times by Ni row. I would obtain, you see, Yi is just this vector Yi1 to Yin equals what? Xi transpose beta. So you see, this is just what I can write as this. So I would just write this as beta 0 plus Xi1 transpose beta to beta 0 plus Xi transpose beta. Okay, that's the fixed part. And for the random part, it's just delta I. But delta I itself is a scalar. So it will appear for Ni times. So I will just write delta I. This will appear for Ni times. And for Ni times. And then lastly, I will stack my epsilon Ij's together, I and I. That's my last part. So you see, this is the matrix form. And how can I convert this into this form? I just need one more step, right? So this matrix can be written as 1 Xi1 transpose to 1 Xi Ni transpose together times this vector beta 0 beta. Because here this beta itself doesn't include the intercept. So that's why it's different, a little different from here. Here it includes the intercept. Plus, for this part, actually, we can just write it as, you see, 1 times delta I, the scalar delta I, plus epsilon I. You see? So I do have that form. Yi equals to a matrix times the fixed design matrix times the coefficient vector plus the random design matrix times another coefficient, random coefficient, plus the error term. Okay, so lastly, let me just give a notation. This is the xi beta. This is just the zi delta I, right? So that's it. That's the random intercept model written in the form of linear mixed effect model. So what I want to say here is that given this model assumption about the random part, given this part, I can see something quite interestingly. So what is the variance of Yij in this linear mixed effect model? Probably it's easier to see here. So you see the variance of Yij only comes from the random part. That is delta I plus epsilon ij, right? It has nothing to do with the fixed part. So it's the variance of delta I plus epsilon ij. And based on their independence, right? Delta I is independent of all the epsilon ij's. So I know I can separate them for independent random variables is equal to the variance of delta I plus the variance of epsilon ij. And I know each one. So it's omega squared plus delta sigma I squared. That's what I have. And then how about the variance, the covariance among the yi something? So for example, two entries in this vector, they don't correspond to the same j, but they are within the same group. Let's take a look. So let's just do variance of yij, sorry, covariance of yij and yik. Let's look at those two. For I doesn't equal to j. For j doesn't equal to k. What would be the covariance of yij and yik? What's in common? You see, delta I is in common. So this is actually the covariance of delta I plus epsilon ij and delta I plus epsilon ik. And by the independence between these two, and between epsilon ij and epsilon ik. So we have independence of all three. So we have say delta I is independent of epsilon ij. Delta I is independent of epsilon ik. And epsilon ij is independent of epsilon ik. So given all the three independence, essentially, this becomes just the variance. I can see it's reduced to the variance of delta I only. And that is just omega squared. So what this suggests is that we do have dependence for observation within each group. This is the within group covariance. And this is meaningful. The reason we want to introduce this is just exactly the reason why we want to consider the group structure. This is by saying that, okay, students from the same school, they are more similar than students from different schools. So this within group covariance is to encourage the students within the same school to be more similar. Okay, now let's take a look at the covariance between two observations from different groups. Let's say here I have I doesn't equal to I prime. Okay, so now let's take a look at covariance Yij and Yi prime. Probably I can see I prime k because the j and k could be the same or could be different, but the groups are different. So now let's use that model to write it out again. Again, the random part only. This is the delta I plus epsilon ij. This is delta I prime plus epsilon I prime k. So now all the four things are independent. Okay, so by all the independence, I am going to have 0. So this means that if observations are from different groups, there is no covariance at all because we're under the Gaussian assumption. No covariance means no dependence. That means independent, while with covariance means dependent. Gaussian has that nice property. Okay, so you see, this is something quite interesting. So if we look at the covariance structure within each group and between different groups, so essentially we would have this interesting result. So if I put if I stack y, okay, if I stack y as a super long vector, that is, if I do this as y1 to yn. So this is for group 1 with n1 observation. This is for group n with n observation. Then the covariance matrix of y would be what? It will be a block structure like this. So for the top left block, I'm going to have it as, okay, so omega squared plus sigma 1 squared. Omega squared plus sigma 1 squared. That's in the diagonal. For everything in the off diagonal, there will be omega squared, omega squared. That's the first n1 by n1 block, okay? And for the last nm by nm block, I'm going to have omega squared plus sigma n squared, omega squared plus sigma n squared, and omega squared in the off diagonal, in the lower block. And everything else is just 0. So that's my covariance structure for the response. So you see that for each observation, it is most similar to itself, right? That's just its own variance. And its covariance with anyone else in the same group is omega squared. That's for the within group dependence. And it has no correlation with anything outside of its group. So that's why in this random intercept model, there is a concept called intra-group correlation. And this concept is just defined as this, as the Pearson correlation between two observations in the same group. So we can actually define this as the Pearson correlation, okay, between Yij and Yik, for j doesn't equal to k. And we know that this is just defined as by the definition of Pearson correlation, covariance of Yij, Yik. And please know that all the discussion here is on the population, on the distribution, not on a particular sample, right? Because we're talking about the covariance and we're talking about the variance. These are all population level concepts. We don't talk about the calculation or estimation of them on a sample, divided by the variance of Yij, variance of Yik. And you see that by plugging what we calculated here and here, it's simply omega squared divided by omega squared plus sigma I squared. That's the intra-group correlation. So what this means is that if you can estimate omega squared, sigma I squared from your data, you can estimate this intra-group correlation. It gives you the idea of how the observations within each group are similar to each other compared to among other observations. Okay, so do we have any questions about this part? Okay, so now let's move back to our the general case of linear mixed effect model. All right, so we're
Sorry, I have a
still
quick
going,
question.
yeah.
Sorry, were you saying before that usually when people apply this random intercept model, they'll set sigma to be the same across groups?
Mhm.
So in that, so oftentimes in that case, we drop the I for sigma I.
Yes, it's just for the same reason that you don't have so many observations to estimate so many parameters. Just
Okay.
like if you cannot estimate beta 0i under the case that you don't have enough observations, then why would you want to estimate sigma I, right? So it's just that we write a sigma I as a more general notation, but you can always simplify that by removing I.
Okay, thank you.
Yeah. Okay, so now let's move back to the general LMM. So let's just give you a quick recap again. So to compare these two, LMM versus HLM. So in the HLM, we have two levels. The level one is always the within group level. So we write Yij equals to Xij transpose beta plus Zij transpose delta I plus epsilon ij. Okay, I'm writing down the more general notation. So Zij could be a vector containing all the predictors whose effects are assumed to be group specific as delta I. And Xij are the predictors whose effects are assumed to be not group specific, just beta I. And J go from 1 to Ni. That's level 1. And level 2 is on the all groups. So we assume the delta I is equal to some common intercept. So actually, we don't need that, right? Because the common thing is already in the fixed part. So we can just say the delta I itself is following a normal distribution, R-dimensional, with mean 0 and a covariance matrix omega. That's the level 2. So here the I and delta I themselves are IID, and I go from 1 to N for other groups. And here in level 1, I need to say, okay, epsilon ij, they are IID from normal, mean 0, covariance, I can say it's sigma I squared, just to be consistent myself. But you can simplify sigma I squared as sigma squared, right? So sigma squared can be simplified as sigma squared. Yeah, and I would say that's usually the case in application. People do that. Okay, that's the HLM. We have two levels. So combining them into one level, I am just going to have this thing. So just write it as Yij equals Xij transpose beta plus Zij transpose delta I plus epsilon ij. Okay, and here J go from 1 to Ni, I go from 1 to N. And jointly, I would have epsilon I1 to epsilon Ini and delta I. They together are following a normal distribution whose dimension is Ni plus R. So R is the dimension of delta I. So that means I'm going to have a normal with 0 mean vector and the covariance matrix sigma I squared appearing for Ni times and then omega. Okay, so these are Ni times. And I have 0 here, 0 here. That's the distribution. So putting them together, I will write my LMM as this. While in the HLM, I'm going to specify 2 layers of random distribution. One is within group, the other is between group. Or probably it's better I write it this way. Okay, so, or I can write it this way, it's equivalent. This is even more straightforward. That is Yij follows a one-dimensional normal distribution with mean as xij plus, not plus, transpose times beta, that's the mean, and variance sigma I squared. Okay, these are just the independent for observations, random the responses in group I. And in level 2, I am going to have, let me see whether that's okay. Yeah, sorry, my bad. Xij beta plus, sorry, I need to add that, plus, sorry, Zij transpose delta I. Yeah, that's what I have for level 1. And level 2, I will just say delta I, they are IID from R-dimensional normal distribution, 0, omega. Yeah, this is another way of writing level 1. So I have 2 layers of normal distribution. And because here in this level 1, I am going to need that my delta, okay, so basically these 2 levels are combined in this subsequent way. In level 1, so delta I is being conditional on, so it's Bij conditioning on delta I, following this normal distribution. And level 2 is just the distribution of delta I only, and putting them together, I can get a model on the left. So it's just that in this way of writing the model, I avoid the notation of this epsilon ij. I don't need it. I just directly write it as the distribution of yj, just as how we write down the random structure, if you recall. Okay, so now we are going to need to put everything into a big matrix form. Recall that our previous matrix form is just for within group I, right? So let me just scroll down here. You see, this is already a matrix form, but here we just have yi. That's for the ni observations within group I. Now we're going to stack all the observations across all the groups. So then what would we do? So now we have to stack everything. Stack all groups. So we have n groups, I from 1 to n. And now I'm going to give you a notation for the number of observations across all groups. So we denote the summation of ni, I from 1 to n, as capital N. So that's the total number of observations. So then let's first look at the response. The response is, so if you recall, we have this within group I, yi equals to xi beta, the fixed part, plus zi delta I, the random part, plus the random error vector epsilon I. Okay, now we do stacking. So for the response vector y, it's obvious we would just stack them by group y1 to yn. So you see, this gives me a capital N by 1 vector. That's the response. And for the design matrix, since I have a design matrix for each group, but they have the common beta. So you will know after stacking, beta stay as beta, and all the xi's share the same columns. So the x will be stacked by row. It will be x1 to xm. So this will give me a capital N by P matrix. So same P columns, still P columns, but just that I have N1 rows from that design matrix and Nm rows from the last design matrix. Beta stay as beta. And Zi is a little different. So you see, I have Zi times delta I. So delta I is group specific. In other words, each Zi have its own columns to be multiplied by its own delta I. So I couldn't just share delta I across groups. Therefore, my big design matrix for Z is going to be like this. Z1 to Zn. So I'm going to stack them by in the block diagonal way. So you see, this is like N1, this is Nn. But the total here, you see, and the first R columns from Z1, the last R columns from Zn. So in total here, the dimension of Z will be capital N times R, because the R columns are going to appear for N times. So that, and then the delta would be delta 1 to delta N. So this will give me R entries, this will give me R entries. So the total is NR by 1. That's the delta. So you see, by matrix multiplication, you see, when I do Z times delta, I will get Z1 times delta 1 plus Zn times delta N. That's what I will get. The reason I cannot do the same as for X is just because delta I's are different. They are not the same. And then finally, epsilon is obvious. I just stack epsilon 1 to epsilon N. This will give me an big N by 1 matrix. So you see, with this matrix notation, I can stack all my groups together. So I have a common matrix formula for all groups. So that will give me, I can write Y equals X beta, beta is the same beta, plus Z delta plus epsilon. So as a reminder, the dimensions are N by 1, N by P, P by 1, N by NR, NR by 1, N by 1. So that's the matrix notation. Do we have any questions? Okay, that's just the first level. When we write this down, we need to specify the randomness, right? So this is with all the notation, and we have random quantities as the delta, as the epsilon. So how do we proceed? We need to specify the joint distribution of epsilon and delta, which we already have. So what is the distribution of epsilon and delta? Recall that their dimension is epsilon is capital N dimensional, delta is N times R dimensional. So their joint distribution would be normal, multivariate normal with a mean 0, whose dimension is capital N plus NR, and the covariance matrix. So one way to write it down is to look at what's the definition of this epsilon. It's epsilon 1 to epsilon N, and we have independence between groups. So therefore, for simplicity, we could just write it as, okay, so this is just epsilon 1 to epsilon N. Block diagonal within each group is epsilon I, okay, and 0 here, 0 here. And delta, what's that? Delta 1 to delta M. For each delta I, we used to write its covariance matrix as omega, if you recall. So then we could just write omega for N times. So 0 here, 0 here. So that will be that covariance matrix. But we can also simplify it as always. So we can say simplification. I'll just write down the most simplified way. So we could just assume epsilon 1 to epsilon M are all just, well, maybe I shouldn't write it the same. Sorry, I think that's bad. So I should write, maybe I can assume epsilon 1 is just equal to sigma squared times the identity matrix with dimension N1. And epsilon N is just sigma squared with identity matrix with dimension Nn. Okay, that's the simplified, most simplified version. And I could assume that all the omegas are just omega squared with identity matrix are dimensional. I could also assume that. So see, if I do this, I basically reduce this layers of the parameters in this layer just to two single parameters, sigma square and omega square. That can greatly reduce my number of parameters. And then what else? The only parameter I'm interested in is beta, p by 1, the usual parameter we're interested in. Okay, so just to simplify this notation a little bit, so in the later discussion, we are going to denote this as a normal distribution, zero mean, and for the covariance structure, we just denote it as R and G, 0 and 0 here. So with this notation, you see R by its definition is a capital N by capital N matrix. G by its definition is an NR by NR matrix. Okay, so we're going to use capital R to denote this covariance matrix of epsilon and G to denote the covariance matrix of delta. So R is just I write variance epsilon, right? By a vector, then the variance means the variance covariance matrix. G is the variance of delta. So NR by NR. This is M, capital N by capital N. So I'm just going to use this notation for simplicity for our later discussion. Do we have questions so far?
Can I ask a quick question?
Yeah.
Is the big omega, is it a diagonal matrix? Because within the groups, they are correlated, no?
Omega has nothing to do with the observation within a group. Omega is an R by R matrix. It's about the R random effects within a group. So for example, though, if R equals 1, that's just what so if it's a random intercept model, then it's just R equals 1. We have only one random effect. But if you can consider R, so for example, if you consider the intercept is random and a slope is random, then R equals 2. Then this by assuming how you assume those two random effects are dependent on each other. But yes, often we assume omega is diagonal. So that is, we don't consider the dependence between random effects for simplicity.
Okay, thank you.
Thank you. Yeah, so that's a very good question. Yeah, we just need to bear in mind that what those random quantities are actually about. So if you have any questions, please feel free to raise your hand anytime. Okay, so
hi, Professor. If our interest is only beta, can we see like just LMM just as a way to assign a structure on the random noise and
yeah,
don't care
exactly.
too much about? Okay.
Yeah, exactly. Yeah, so basically that's something we will see very soon. So you are just basically assigning the randomness by group structure by assuming that within each group, the observations are more correlated. The error term within group are more correlated within each group.
Okay.
Yeah. Okay. So, and also Kangcheng, as you know, I'm just going to make a case here. So you know, in statistical genetics, many people put a lot of the predictors, many predictors they want to use into the Z matrix. But they realize that, okay, because the Z is a very high dimensional matrix, which means that the NR is super huge, NR is super huge. So in that case, this delta, although it's something that must be considered, it is not really estimable, right? So you don't have enough observation to estimate those. So that's why in that people also assume delta to follow a normal distribution, just to reduce the number of parameters.
Yeah, thank you.
Yeah. Okay, so a model, yeah, so this is the model. So now let's take a look at the model in 3 different ways. So this way, by writing down the model as this form and by specifying the random structure is what we call model 1. So we'll say there are 3 ways to write this model. So the first way is what we already did. So we just write y equals x beta plus z delta plus epsilon with epsilon delta following normal mean 0 covariance matrix RG. Okay, we just restate what we said. That's the first way. And the second way is that we can directly write it down as the hierarchical linear model. So this is the linear mixed effect model way. The hierarchical linear model way is that we write y given delta following normal distribution with x beta plus z delta, and the covariance matrix is only from epsilon. So the covariance matrix is R. That's the level 1. Level 2 is delta following normal distribution with mean 0, covariance matrix G. That's the second way of writing down the same model. And this is the HLM way, hierarchical linear model. And there's a third way. The third way is that we could just consider Z delta plus epsilon as one random error term. So the third way is we write y as equal to x beta plus epsilon star with epsilon star just equal to z delta plus epsilon. Okay, so if we write this way, then we are trying to put ourselves as a linear model, but we put these two random terms into a common random error term. Then let's take a look at the covariance matrix of epsilon star. Remember, if we're on the linear model, then we call this epsilon, right? And epsilon, we know in the linear model, its covariance matrix is just sigma squared times identity matrix. That's what we have. But now let's take a look at here. So for this epsilon star, if we take a look at its variance, then we need to consider its definition, z delta plus epsilon. So we know that by independence between delta and epsilon, right? This is what we assume. This can be written just as the covariance matrix of z delta plus the covariance matrix of epsilon. And don't forget that these are all capital N by capital N matrices. Okay, and then by the matrix formula for the covariance matrix, we know this is equal, the first term is equal to, because Z itself is a design matrix, that's fixed, we get it out. So Z times the covariance matrix of delta times Z transpose. That's for the first part. The second part, we know it is R, right? So R is an N by N matrix, as we have seen here. And for this part, Z is what? We know Z is N times big N times NR. And of course, its transpose is NR times big N. And the covariance of delta we know is G. So we get it out as Z times G, Z transpose plus R. So essentially, this covariance matrix is just having two parts. One is from the contribution of random effects. The other is from the contribution of the random error. And if we use the simplified form, you can see what it will look like. So in the simplified form, in the most simplified form, okay? I will say most simplified form, what is G? G is just omega squared times identity matrix with NR dimensional. And R in the most simplified form is sigma squared times identity matrix with capital N dimensional. So in this case, you would see that what is the variance of the epsilon star? So because this is just identity matrix times a scalar, I can get a scalar out. So it's just omega squared times Z transpose plus sigma squared identity N. That's it. So therefore, you see, in the random intercept model, what is Z? In RIM, Z is just a vector of ones. And that vector of ones has capital N dimensional, right? So, oh, actually, my bad. No, it's not this. It's this. It's this one with N one dimensional to one with N dimensional. It's like this. So it's actually capital N by N dimension. That's Z. So you see, what would happen if I have Z times Z transpose? It will actually be this. So Z times Z transpose, this will give me an N by N matrix, capital N by capital N matrix. This will actually be, it's just a matrix of all ones. So I have all ones here with N1 by N1 dimensional. All ones here with N by N dimensional and 0 elsewhere. So then you see omega times this matrix will give me like a block of omega here, a block of omega here, omega square here, and 0 elsewhere. So essentially, this variance of epsilon star will be equal to, I can directly write it down. So it will be omega squared plus sigma squared throughout the diagonal, okay? But I would have within each block, omega squared elsewhere, omega squared in the off diagonal, but zeros between blocks. So you see, that will be the structure. So in other words, we are assuming the random terms within each group have covariance omega squared. And between groups, there's no covariance. So that's essentially what the random intercept model gives us. So basically, you see, this can be considered as a case of the what we call a heteroscedastic linear model, which means that the random error terms are no longer IID with common variance, but there is dependence between random error terms within each group. Does that make sense? So these things are actually connected. What we talked before about that, okay, if you recall, when we talked about weighted least square, we said that in the weighted least square, that's a special case where our random error terms still are independent, but each of them have a different variance sigma I squared in that weighted least square. So we said that if we know those sigma 1 squared to sigma n squared, we could take their inverse, put them into that weight matrix, and then we can do the weighted least square. That's just a way to connect to our iterative reweighted least square algorithm. That's something we said before. But here you see also when our random error terms are not just sigma squared times identity n. When we don't have that, we need to consider this into our estimation of beta, because beta is ultimately our parameter of interest. Okay, so that's the third way of representing the same model. You can see that in the third way, you basically condense the two random terms into one term. And from now on, we are going to give this sum a notation. We're going to denote it as V. V is an n by n matrix for simplicity. So if we don't want to distinguish G and R, we're going to use V. So just keep in mind. So to summarize, we can say, okay, to summarize, the third way of writing the model is that y equals x beta plus epsilon star, with epsilon star follows normal distribution with mean 0. This is capital N dimensional, and V as the covariance matrix. Okay, so then what are the advantages of using each model? So if you're only interested in beta, you can use either one or any of those because they all include beta. But if this random effect vector delta, which is n times r by 1, if this delta is also something you want to talk about, then you must use the first two ways, not the third way. Because in the third way, delta disappeared. Essentially, when you write it out, you are using the marginal model, right? For y only, and there's no delta in the model at all. So the third way will not give you any information about delta, but the first two ways are going to allow you to talk about what the distribution of delta is given my data, just like the Bayesian framework. We want to talk about the posterior distribution of a parameter, of a random parameter given data. And with the first two ways, we're still able to do that, but not with the third way. Okay, so then what I want to say is that if we want to talk about the distribution of delta given my data. So here my data has three parts, y, x, z, right? The two design matrices and my response. Then use the first and second ways. But if we're only interested in data, we could use the third way. Okay, do we have questions? Okay, so if not, let's continue. So now we're going to talk about the most difficult part for LMM. How do we estimate parameters? Like parameters in LMM. So of course, the most interesting parameter is beta, right? The key parameter is beta, which is p-dimensional, as always. But there are also some parameters we must consider about. So other fixed parameters so it could be V if we're under model 3, or G and R if we're under model 1 and model 2, right? So it could be this or those two covariance matrices, or if we use the simplified version, not G and R, we can just reduce it to omega squared and sigma squared, right? So these are the fixed parameters we must estimate. And furthermore, if we want to talk about that intermediate random parameter, delta, we may also do it. So, and other random parameters. For random parameters, we do not really talk about a value for it because it is random. But under the Bayesian framework, we can talk about its posterior. So in this case, it will be delta, right? And delta itself is combined from n delta i's. So this is actually delta 1 to delta n. Each is r dimensional. So we can also talk about this. So you see, these are all the things we can talk about parameters in the LMM. So, you know, in the posterior, okay, the posterior here, I can simplify this notation because x and z in my data are considered to be fixed. So in our class, we consider fixed design from the beginning. So the only random data is y. So we can also simplify this as delta given y only, because you know that for fixed quantities, putting them after conditioning doesn't make a difference. So we could remove them from conditioning. So it's delta given y. And therefore, when we talk about posterior distribution, is what the distribution of delta given y is. And under the Bayesian framework, often we talk about posterior mean. So then what is posterior mean? Posterior mean is the expectation of a random parameter given its posterior distribution. So we can talk about its posterior mean. And then this becomes a fixed quantity we can estimate about. Okay, so what I'm going to talk about first to begin this whole discussion is to make ourselves easy. So we will first talk about estimation of beta and the posterior mean. When our other fixed parameters are known with known G and R. So the variance related parameters are assumed to be known. And we only talk about in this ideal case, how do we estimate the effects? One is the fixed effects, the other is the posterior mean of the random effects. Okay, once we can sort out this problem, then the next is that how can we estimate G and R? And then we're going to do plugin. So we just decompose the estimation into a two-step thing. So first, let's take a look at beta. So you see, in this case, our third way of the model will help us a lot, right? Given this model, y equals x beta plus epsilon star, with epsilon star following this, and now v is known because v is just v times g times z transpose plus r. So they're all known. So this tells me, okay, v equals v g z transpose plus r is known. So given a known v, how do we estimate beta? Actually, we know how to do it. So by the MLE, we know how to do it. So basically, we can easily show that. So from 3, right? Given this model, we can write down the likelihood of beta. We can show that beta had MLE by maximizing this likelihood would just be the weighted least square formula. So it's actually x transpose v inverse. Okay, v is the variance. We are doing covariance matrix. Take its inverse, x inverse times x transpose v inverse y. So this is the weighted, it's a more general case of the weighted least square, right? Because here the weights are no longer diagonal, but we still take the inverse anyway. So this can be shown as the MLE. So you see, the third way has its advantage. It can give us a very simple formula for estimating beta. But how about this posterior mean? So for this one, we cannot use 3 because, as I said, in the third way, the delta is disappeared. So we need to use the first 2 ones. So we are going to use the second way of representing the model. Okay, so from the second way, what we're going to do? We're going to derive the distribution of delta given y from the second way. To derive the distribution of delta given y. That's what we are going to do. So what's the idea behind this? The idea is that from these 2 layers, we can easily get the joint distribution of y and delta. And then, given the joint distribution, which is still Gaussian, right? What's the dimension? Here is capital N dimensional. Here is m times r dimensional. Putting them together, the joint distribution will be capital N plus nr dimensional. Then, given joint Gaussian, I inverse the conditioning relationship. Then delta given y is still a Gaussian. And that's it. So I know that's what I would expect. Okay, so then what do we do? So we start from 2. Let's try to get the joint distribution of y and delta to start with. So like I said, this is capital N dimensional, this is nr dimensional. Their joint distribution, the mean of y is obvious, that's x beta. So it's not 0, but the mean of delta is 0. So still, this is capital N, this is nr. The covariance matrix. The covariance matrix for y, it will have 2 parts, right? So it's just V. I know that This Y's covariance is V from the third way, from the third way of writing the model. The covariance of delta is what? Is G. That's what we have from RG. But what's the covariance between Y and delta? That's something I need to calculate. So the covariance matrix of Y and delta, I need to derive it from the model formula from here. From the first model, I can derive that. So you see from the first way, I can write Y as X beta plus Z delta plus epsilon and delta, you see. And epsilon is independent of delta. The fixed part can be removed. So because of this, this is just the covariance of Z delta and delta. And then I know this is just Z times the variance covariance matrix of delta, right? I get Z out, and it's just ZG. Let's check dimension again. This is capital N by NR. G is NR by NR. So we're good. So the covariance between Y and G is actually ZG here, okay? And what we have here is just its transpose. So it's G transpose Z transpose. So we get its joint distribution. It's still normal, multivariate normal. And then we would just derive the distribution of delta given Y. And we actually have a formula for that by inverting the normal distribution. So we have it in the notes. How do we inverse the relationship? But basically, you can regard this as, okay, for the mean part, I'm going to just do the regression of delta on Y. And that's actually very similar to the least square formula we have seen before. But I'm going to skip the details. So we can actually derive that, okay, this is still a normal distribution with a mean, with a covariance. And what I need is just this mean. This is what we call the expectation of delta given Y. I'm just going to write down the answer directly. We can show that given this formula, it will be equal to G times Z transpose times V inverse times Y minus X beta. So this is the posterior mean of the random effects. But again, this expectation for the posterior involves unknown parameters, right? Here, the only unknown parameter is beta because G is known, V is known. So we just plug in the NLE for beta. So plug in beta hat MLE. We obtain an estimator for the posterior mean. And this thing actually has a name, okay? So we give a notation first. The notation is our estimated expectation of the posterior expectation, estimated posterior expectation. And it's just GZ transpose V inverse Y minus X beta hat MLE. And it has a name as a jargon. So this thing is called the best linear unbiased predictor. Okay, so short as BLUP. Best linear unbiased predictor. But I think if you don't know this jargon, it's totally fine. We can just say, okay, it is the estimated posterior mean of the random effects in just a term in the linear mixed effect model. Okay, so, oh, sorry, I should say this is the empirical version. Yeah. So the BLUP refers to this unobserved one. I should put it here. This is the BLUP. And the empirical version of that, I add an E here. So this is the what we actually obtain from our data by plugging the estimator. Okay, so we'll stop here for today. We have talked about the matrix notation for all the groups together. This is just the most general notation. And all the linear mixed effect models can be considered as special cases. And then we talk about under this set of general notations, how do we estimate the key parameter beta by MLE, assuming the covariance matrices are unknown, the ideal case. And then we talk about if we are interested in the random effects, it's posterior mean. How do we do it? So next time when we come back, we'll talk about where the G and R being unknown, how do we deal with those? Okay, so that's all for today. Let me start the recording. And also for the announcement, we want to say that for the final project, I still got questions about what it is about. Just to re-emphasize that the scope, we want every group to write about a survey paper related to our class. So for example, I have heard that some students choose to write about Bayesian linear models and this relationship with causal inference. I think it's a very interesting topic. And for some good references, please check the survey papers I posted on CCLE from my other class last quarter, so you can get a sense about what the survey paper should look like. So if you haven't signed up the group or you didn't receive the order for your presentation in week 10, please actually contact me immediately so we can add your name. All right, so that's all for today.
Thank you.
Thank you.